Hello everyone, this is Mrs. Snook with section 6.3. We're going to do this section over 2 different days. So today is going to be 6.3 day 1. And section 6.3 is about vectors in the coordinate plane. And our objective is we're going to represent vectors as directed line segments. We're going to write component forms of vectors, and we're going to do some vector operations. So first up, we need to have some definitions. So a vector is a quantity that has both a magnitude and a direction. An example of a vector might be velocity, where an air traffic controller has told a pilot, fly your plane at 600 miles per hour, so that's your magnitude, and go due east. That's your direction. And the way we write a vector is with lowercase boldface letters such as bold U, V, and W. And if you're writing it by hand, you would do U with an arrow on top, V with an arrow, and W with an arrow. A vector can be thought of as a line segment, so remember back in geometry, line segments that have a specific direction. And here's some definitions of on a vector. The initial point, that's where your vector starts. And this is often called the tail. And then the terminal point is where it ends, and that's where the arrow is going to be. So if you look here, I have drawn us a vector starting at the initial point, goes to the terminal point. Magnitude is how long it is, and the direction is the direction it's going in. Now we have a formula that we can use for the magnitude of a vector, or the length. And our notation is going to be these 2 double bars, and then the name of the vector, and then the double bars. So this symbol here means length. And what you're going to do is you're going to subtract your x coordinates, and you're going to subtract your y coordinates. This is based on the distance formula that you've been doing since geometry. So let's do our first example. We're going to show that vector u, which starts at P and goes to Q, is equivalent to vector v that starts at R and goes to S. So the first thing I'm going to do for checking equivalence on the vectors is I'm going to check their magnitude and make sure they're the same. Because if they're equivalent, they should have the same magnitude and the same direction. So let's do the magnitude first of vector u. So I'm doing that double bar to indicate I'm doing magnitude. Put in big square root. And let's do the Q1 minus P1. So I'm going to do 3 minus 0, and that's squared. And then the other ones are going to be 2 minus 0 squared. So that's going to be the square root of 3 squared is 9, plus 2 squared is 4. I'm going to get the square root of 13. That's our magnitude of vector u. Now let's do vector v. And I'm going to do 4 minus 2, and the other 4 minus 1. So 4 minus 2 is 2, square that, I get 4, and then 4 minus 1 is 3, I square that, I get 9, so I get square root of 13. So okay, they both have the same magnitude. Check. Now let's check their directions. Easiest way to check direction is to use the slope. So now I'm going to do the slope of vector u. So my slope of vector u is going to be 2 minus 0 over 3 minus 0. I get 2 over 3. And now do the slope of vector v. 4 minus 2 over 4 minus 1. I get 2 over 3. So I have the same direction now. So we know that vector u and vector v are equivalent. I probably spelled that wrong. I'm just going to do it like this. I'm going to say vector u equals vector v. Okay. Now the next thing we're going to do is we're going to find a vector in component form. Now the components simply mean if I start at my starting point, how far up do I have to go, and then how far over do I have to go. So what I'm showing you in red are the actual components of this vector. Now the easy way to find your components of the vector is literally take that vector and slide it to the origin. And then the point where its terminal side lands, where that terminal point is, that will give you the values to put in your vector for the components. So what I'm going to do is, I've already given us a coordinate grid here, and I'm just going to slide this vector where it starts at the origin. So I'm putting in my xy coordinates. My origin is going to be right here. So here's my x-axis, here's my y-axis. Now I'm starting at the origin at 0, 0. And then P was at 4, negative 7. So to move it to the origin, I have to move it back 4. So now I'm going to take Q. I'm going to move that one back 4. So it's going to end at negative 5. So negative 1, 2, 3, 4, 5 along here. So Q is going to land on this dashed line I'm drawing in. And then for the y coordinates, it was negative 7. I had to move that up 7. So I'm going to move my P. It was at 5. I've got to move that up 7. So that's going to put it at 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so my new terminal point is right there. I'm going to sketch in my vector. Okay. So now the coordinates here are negative 5, 12. So when I go to write this vector as in coordinate form, component form, I'm going to say that PQ equals, and we're going to use brackets, so PQ equals, in brackets, negative 5, 12. And what that means is when you write the components of the vector, your horizontal component is going to go 5 to the negative, and your vertical is going to go 12 to the positive, just like here. Now here's an easier way to do this. Instead of literally sliding it, you can also just find the difference in their coordinates, and that will give you the component form. So let's try it on these. We're going to have vector v, and this time I don't have a graph of it, I just have the coordinates of the start point and the terminal point. And all I'm going to do is I'm going to find the difference between them. So for my x, I'm going to do 8 minus 3, so I get 5. And then I'm going to do 9 minus 6, so I get 3. So now my components are 5, 3. Actually, let's go the other way. We're going to start at P. That was starting at Q and ending at P. So start at P to get to Q. That's right, you add 5. And then starting at P to get to Q on you have a -3. So I have to go up 5. I have to add 5 to get to 8. So there's my 5. I have to subtract. I have to add 3 to get to 9. I had it right first. I apologize. All right, now for my next vector v, which starts at A and goes to B. So to go from -8 to -3, you have to add 5. To go from 4 to 3, I add 7. So each time, all I'm doing is finding the difference between those coordinates, and that gives me my component form. Here's another one, vector xy. Let's do the x's. So I have a 6 minus 1 gives me 5. And then a -4 minus a -7 is 3. And then st, they made this one easy because they put it in the standard position. Because its initial point is at the origin. So then all I have to do is read the coordinates of its terminal point, 5, 3. So notice the components of all 4 of these vectors are the same. That means all 4 of those vectors are equivalent to each other. All right, the last thing we're going to do is some scalar multiplication and vector addition. And I'm going to do it 2 ways. First way, we're going to do it graphically. And then the second way, we're going to do it, I guess algebraic is the way to say it. So the first thing is 2v. So we're going to take vector v and we're going to double it. We're going to have 2 of them. So I could write this as vector v plus vector v. And I'm going to use that idea when I do this graphically. So my components for vector v are -2, +5. So I start here at the origin. I go -2. I'm going to go up 5. 1, 2, 3, 4, 5. There's my terminal point. So this is vector v. That's one of them. Now I've got 2 of them. So from this midpoint here, I'm going to go another 2 back and then another 5 up. And this is my resultant vector. I'm going to highlight it. I'm going to use my highlighter. And it ends at the coordinates 1, 2, 3, 4. So this is -4 and 10. So that's doing it graphically. And when you add 2 vectors together, you want to line them up tip to tail. So I want you to notice that what I did is I took the tail of my second vector and I put it right where the tip of the first one is. And then wherever you end up, you start at the origin and go to wherever that ending point is, and that's your resultant vector. So tip to tail. Now let's do it mathematically. I know vector v is -2, 5. Now when I multiply this by a scalar, so 2 times vector v, that's the same thing as 2 times its components. So I literally think of this as distributing. So my 2 vector v is -4, 10. Which is exactly what we got doing it graphically. Next one, we're going to do vector w minus vector v. Now I want you to remember that when you subtract, that's the same thing as adding a negative. So I'm going to plot a vector w, and then I need to do vector v, and I need to flip it around backwards, and then put that tip to tail. So let's get w. W is 3, 4. So I'm going to go over 3 and up 1, 2, 3, 4. Here's w. Okay, now vector v. Vector v is negative 2, 5. So when I flip this around, I'm going to do the negative of it. I just do the negative of both things inside of the components. So my negative of vector v is going to equal 2, negative 5. So now I'm going to start, I'm going tip to tail, so I'm going to start here at the tip of vector w, and I need to go 2 positive, and then I need to go negative 5. So 1, 2, 1, 2, 3, 4, 5. So right here, this is negative vector v. That one is vector w. Now my resultant vector starts at the origin and goes to the terminal of that last one. So that one in red, that is vector w minus vector v. And the coordinates where we end are at 1, 2, 3, 4, 5, negative 1. Okay. So the key to subtracting is flip that second vector around and then add. So now let's do this algebraically. Vector w plus a negative vector v. Here's vector w, was 3, 4. And I already wrote my negative vector v in component form, so I'm just going to add 2, negative 5. So I'm going to add my 3 and my 2, and I get a 5. And then I'm going to do 4 plus negative 5. There's my negative 1. So now doing it numerically, I have vector w minus vector v is going to be 5, negative 1. Got the same thing both graphically and numerically. Last one we're going to do is we're going to add vector v to 2 times vector w. So just like before, I'm going to plot vector v, and then I got to get that double of vector w and plot that one. And I'm going to go tip to tail. So vector v was, I got to go back and get it, negative 2, negative 5. I'm just going to write it here so I don't keep forgetting. Was it negative 5? Positive 5. And then vector w is going to be 3, 4. Okay, so let's do this graphically first. So I'm going to plot vector v. I'm going to go back 2. I'm going to go up 5. 2, 3, 1, 2, 3, 4, 5, right there. So here's vector v. Now I got to do 2 w's. So I'm going to go positive 3, 1, 2, 3, 1, 2, 3, 4. There's 1 w. Now I got to do my other w. 1, 2, 3, 1, 2, 3, 4. I went a little bit off my grid, but that's okay. And then my resultant is this one. So this is vector v plus 2 times vector w. That's our graphic method. And now let's do it numerically, which I personally find numerically to be much easier. So vector v plus 2 times vector w. V in component form is negative 2, 5. Now I need to multiply vector w by the scalar. So I get negative 2, 5 plus 6, 8. And then negative 2 plus 6 is 4. And then 5 plus 8 is 13. So here's our answer in component form. And that's not a 7, that's a 13. Okay. So last thing I want to show you is some properties of vector addition and scalar multiplication. And we've used some of these. The first one says that if I'm adding vector u and vector v, that's the same thing as if I add vector v plus vector u. So the order that you add your vectors doesn't matter. The second one talks about adding 3 vectors together. Now I can add the first two u and v and then add w, or I can add v and w and then add u. Again, order doesn't matter. Third one basically says that if you have a 0 vector, and this 0 vector would be 0, 0 in component form, then if you add that to a vector, you just get that same vector back. And then the fourth one, this is if I add a negative vector, then I get that 0 vector back. Fifth one is, let's say I do a scalar times a vector. I can multiply that scalar times the vector first and then multiply by another scalar, or I can multiply my 2 scalars together and then do the vector. Second, number 6, this one is distributing. So c plus d times vector u is c times vector u plus d times vector u. So our distributive property works. It also works when I'm multiplying, or just when I'm multiplying 2 vectors that I've added by a scalar. So I can distribute scalar times a vector and scalar times a vector. This one just says that if you multiply 1 by a vector, you get that vector. And then if I multiply 0, so I do a scalar 0 times a vector, then all those components will come out as 0 to get the 0 vector. And then our last one, what this says is if I take the magnitude of a vector that I've multiplied, it's the same thing as getting the magnitude first and then multiplying. So I can multiply my vector and then calculate its magnitude. I'm going to get the same thing as if I calculated the magnitude and then multiplied. So these are some properties that you can use when you're working on your vector operations. And that is it for today. Thank you for watching, everybody, and have a great day.